Welcome to the Explainer. You know, if you're a researcher, then you are dealing with data, lots of it, and understanding the true shape and structure of that data is absolutely critical. That's where linear algebra comes in, and today we're going to demystify two core concepts, dimension and rank. We're going to transform them from these abstract, kind of scary ideas into powerful, practical tools for your research. So, let's dive in.
So let's start with a really fundamental question. Just imagine you have a space. It could be a simple plane, or it could be a super complex data set with hundreds of variables. Now, inside that space, how can we describe any single data point, or what we call a vector, in a way that is totally unique? No confusion, no ambiguity. That's the problem we're setting out to solve right now.
And here's our roadmap for today. We're going to build these ideas one on top of the other. We'll start with why we even need this first tool, then see what that tool lets us build. After that, we'll figure out how to measure things with it, and finally, we'll see this amazing theorem that just ties everything together beautifully.
To get that one-of-a-kind description, it turns out that just having a set of vectors that can span the space isn't quite good enough. Yeah, it can build every vector, but it might give you multiple ways to do it, which is messy. What we really need is something called an al-asas, or a basis. A basis is so crucial because it guarantees that every single vector has one and only one unique description. It's what takes us from total ambiguity to perfect clarity.
So, what's the secret sauce? What's the magic ingredient in a basis? Well, it's a property called linear independence. And the logic here is actually pretty cool. If you could somehow describe a vector x in two different ways, you could just subtract one description from the other. What you'd be left with is a mix of basis vectors that adds up to 0, but not all the weights are 0. And by the very definition of linear independence, that's impossible. This property is our absolute guarantee of a unique address for every vector in our space.
Okay, so a basis gives us a unique address for every vector. Now let's see how this creates something we're all really familiar with, a coordinate system, or a نظام الإحداثيات, or a coordinate system. This is where we get to build a totally unique grid for our subspace. For any basis B you pick, those unique weights you use to build a vector x are called its coordinates relative to that basis. And when you just bundle those weights together into a single vector, you get what we call the متجهات الإحداثيات, or the coordinate vector of x. Think of it like the exact recipe for building your vector x using your specific basis ingredients.
So how do we actually find these coordinates? Well, it's a process you're probably already familiar with. First, you set up a simple vector equation. Then, you can represent that as an augmented matrix. You row reduce it, and boom, the solution gives you your unique weights. In this case, they're 2 and 3. And there you have it, the coordinate vector relative to our basis B.
And this is where it all clicks. This is the big picture. Even if your subspace is some weird tilted plane living in a high-dimensional space like R3, the basis lets you just kind of slap a familiar grid onto it. It makes that complicated subspace look and act just like the simple R-square we learned about in high school. The fancy name for this amazing one-to-one mapping, this correspondence that preserves all the structure, is an isomorphism.
All right, so if a basis gives us the structure, the grid, for a subspace, how do we measure the actual size of that subspace? You know, is it a line, a plane, or something much, much bigger? This brings us to the concept of al-Bu'd, or dimension.
And the definition? It is just beautifully simple. The dimension of a subspace is just the number of vectors in its basis. That's it. If your basis has 2 vectors, congratulations, you've got a 2-dimensional subspace. For you, as a researcher, this tells you the exact number of independent variables you truly need to describe your system. The hard part is finding the basis. Counting the vectors is the easy part. And this leads to an incredibly practical shortcut for finding the dimension of 2 of the most important subspaces connected to any matrix. For the fضاء al-amud, the column space, its dimension is just the number of pivot columns. And for the fضاء al-sifri, or the null space, its dimension is the number of free variables, which are your non-pivot columns.
Now let's build on that idea to define a very closely related concept, one that focuses specifically on the matrix itself. This is the rutbة, or the rank of a matrix.
The rank of a matrix is simply the dimension of its column space. So what does that mean in practice? It's just the number of pivot columns in that matrix. This single number is so important. For your data matrix, it tells you the number of truly independent features you're working with. It's a measure of the complexity and non-redundancy in your data. And finding the rank? It's a process you already know how to do. You take your matrix, you reduce it to echelon form, and you just count the pivot columns. In this example, we find 3 of them, so the rank of matrix A is 3. It's as simple as that.
Okay, now for the most elegant part of this whole story. It's how the dimension of the column space, which we now call the rank, and the dimension of the null space are connected. They aren't just 2 random numbers. They are perfectly linked by an absolutely beautiful and fundamental theorem.
And here it is, the rank theorem, or نظرية رتبة. It says that for any matrix A with n columns, its rank plus the dimension of its null space will always equal n. Think about it. The number of pivot columns plus the number of non-pivot columns has to equal the total number of columns. It's a perfect statement of balance that exists inside every single matrix.
Let's see this in action with that example from before. Our matrix had 5 columns in total. We found its rank. The number of pivot columns was 3. That left 2 non-pivot columns, which means the dimension of the null space is 2. And what do you know? 3 plus 2 equals 5. The theorem holds perfectly. It always does.
So here's the big takeaway. These concepts aren't just for describing things. For you, as a researcher, their real power comes from being incredible diagnostic tools. They give us powerful new shortcuts for understanding the fundamental properties of a system, like whether or not a matrix is invertible.
Which brings us back to that giant of linear algebra, the invertible matrix theorem. All of these concepts we just learned, basis, dimension, rank, they add powerful new equivalent conditions to this theorem. Just look at statement P. For an n by n square matrix, if its rank is n, it's invertible. Period. That is an incredibly fast and powerful way to check one of the most important properties of a matrix.
And this brings us to one last thought, especially for those of you working with real-world data. In the textbook, all our numbers are perfect. But in the lab, with measurement errors and computer arithmetic, a number might be really, really close to 0 without being exactly 0. So the question is, how do you determine the effective rank of a matrix from messy experimental data? That is a crucial question in applied fields and a perfect topic for you to go explore further.